Hello everyone, this is Feridon Tavasoli and welcome back to our electrical channel. And this session we'll be talking about electric power. In this session, by the end of the lesson, you should all be able to define different types of electrical power, define the difference between them, define power factor, and explain why it's important to improve it. Some of you will be able to explain how we can save on our electricity bills, and also write the equations for all types of power. Elements of an AC system. In an AC system you have three elements usually. Resistor is the main part, which you always have inadvertently, and inductor, which is shown by this symbol, and L is this the letter for it, indicating inductance or inductor, and C is the capacitor or capacitance, and this is the symbol for it. Now, capacitor itself is not there in every single AC circuit on its own, unless you deliberately put it there, or you're dealing with very high frequency circuits. Right, don't get too confused. I'm only trying to break it down into bits in a minute, so it's not going to be overwhelming. Resistance or resistor is a part of the circuit that's always there in any circuitry, like a circuit with just a lamp there, or a heater, or a motor. You always have a resistance there. Inductor, with most AC appliances, you will always have an element of inductance. And capacitor is another component that we deliberately put there to counteract with the effects of inductors, with bad effects of inductors, if you like. And the supply voltage, because it's AC, we're dealing with AC in this session, so this is the symbol for it, and it's still V, a dedicated letter for it. Types of electric power. You have three different types of power. True power, which is shown by P, or capital P, the measure of the power used when considering resistance only. So the power that's consumed only by that resistor in that circuit that I showed you. It is measured in watts, and the letter for it is W, or kilowatts, kW. The other type of power is reactive power, and the letter for it is Q, and is measured in volt amp reactive. It is the measure of power in terms of inductance or capacitance. So the other two elements that we had in the circuit, inductance or capacitance, they consume a different type of power, which we call reactive power. It's not the power that actually does something for you. Like, for instance, if you have a lamp, it's not the brightness of it. It's that little coil inside there, the filament, the wire inside the lamp that actually gives the brightness, but also because of the coil, because of the shape of the wire, which is almost the same as a coil, and the frequency of the voltage, it causes that electromagnetic field around it, and it causes heat, so the energy is used in different forms. That is your reactive power for that lamp. If you have a motor, for instance, you have a lot of wire winding inside the motor, and because of that you have magnetic field, and you need the magnetic field to turn the motor, but at the same time there's a lot of magnetic field. We don't really need that. We don't need the effect of it, the reactive part of it, but we need the rotation part of it. That rotation, that is acting as a resistor in the circuit, but the magnetic field is acting as inductor, if you like. Very simply put there. It's more than this, but I'm just trying to make it as simple as possible so you understand three different types of power. So true power, reactive power, and the other one is, and by the way, reactive power is measured in volt amp reactive or kilovolt amp reactive. and the other one is the apparent power, and it's shown by S, and it's measured in volt amp or kilovolt amps. It's the measure of the combined effects of resistance and reactive power, or resistive and reactive power, both the true power and the reactive power both together. Two of them together combined is measured in volt amps or kilovolt amps. At a glance, again, we mentioned the different types of power, symbols for them, and units for them. So true power is shown by P, and is measured in watts or kilowatts. Reactive power is shown by Q, and is measured in volt amp reactive or volt amp reactive. Apparent power is S, and is measured in volt amp or kilovolt amps. Now you have a triangle, a power triangle. The true power, the green vector or phasor diagram, the phasor, the green phasor for it is the true power or real power, and is measured in, as you see, kilowatts or watts, and that is the power that you actually use with any appliance that you have at home or industries. The power that you actually use is the green one, P, in watts. Q is the reactive power, is on the y-axis rather than x, because it's the reactive power. It's the power that you're not using, you're returning in fact to the supplier. But if you're not taking that into consideration in your industry, wherever you are, or at home, then you might end up paying a lot more for what you're using. So that leads to this power, which is apparent power, S, which is the combined P real power and reactive power. So apparent power is how much you pay, P or real power is how much you use, and this is how much you don't really use but you need it for the appliances or machines to run. There is a way to eliminate that, which is going back to what we mentioned earlier about the capacitors, using capacitors. This effect is caused by inductors. Inductors in the circuit have caused this reactive power. True power is represented by the horizontal green phasor or vector, and it's the real power, and it's measured in kilowatts or watts. The vertical line represents the reactive power, Q, which is generated by the inductor in the circuit, the inductance of the machine or component or the appliance that you have in the circuit. And the apparent power, the line that joins the two represents the apparent power, S. This type of diagram can be drawn either as you can see, top right, or like the diagram shown below. The one below, the load factor can be found. Right, this is the power triangle. The horizontal line or the green phasor or vector represents the real power, P, and which is measured in watts or kilowatts. Q, the vertical line or red one, the red line is representing the reactive power, and it's measured in kilovolt amp reactive or volt amp reactive. And if you join them together, combination of them is the line that joins the reactive power and the true power together. That is your apparent power, S, and it's measured in volt amps or kilovolt amps. Now the apparent power is how much you pay, what you pay for. The apparent power is what you pay for, real power is what you actually use, and the inductive power is what you need for the machines to run, but you don't really need to pay for it because you're returning that to the supplier. It's reactive. It's not something you use. Again, types of power and their formula. The true power is, like we said, we measure it in watts or kilowatts, and the formula for it is volt times current times cos of that phase angle. In this case is the phase angle here between the apparent power and their true power. And we also call it power factor, PF of the angle or power factor. Cos of that angle is power factor. So cos phi is the power factor, not the phi, cos phi. Right, an analogy of true power, apparent power, and reactive power is a beer analogy, which basically is, this is how much you're paying for, what you're paying for. This is what you're paying for. You're paying for a pint of lager, for instance, and what you get is this amount of beer, and the rest is right. We have an analogy, a crisp or beer analogy. A beer analogy is that you pay for a pint of lager this much, but you only get this much beer, and then the top of it is foam. So this is not what you want, but you're paying for it because it's part and parcel of the product. The same with the crisp. You pay for a bag of crisps, but all you get is this much. You're lucky actually if you get that much crisps in a bag, and then the rest on top is the air, and that is the volt-amp reactive as far as electric is concerned, electric power. So that's the reactive power, and the true power is how much you use, and this is how much you pay. Now, so you can see why we need to improve our power factor. To improve our power factor, that means we bring basically this blue vector or phasor all the way down to, or as close as, the green vector. Bring it down to the green, the horizontal axis. So you are basically paying for what you're using. You don't pay this much for what you don't use. So to do that, you have to reduce the phase angle to almost zero. It's almost impossible to bring it down to zero, but it is possible to bring it down. And power factor, like I said before, power factor is the cos of that angle, and cos of 0 is 1. So the best power factor is unity, 1. The power factor, like I said again, to reiterate what we said, is the relationship between the true power and the apparent power. It is the measure of how far the current and voltage of a system are out of phase with each other. By improving the power factor to unity, cos phi, to convert cos phi to 1 or bring it as close as to 1, the apparent power is brought closer to the true power and the current reduces. So the apparent power comes down as close as possible to this, and it also reduces the current, and that sorts the power factor. As the current reduces, so do the cable sizes. As the current reduces, so do the cable sizes and the switch gear, and that again is another saving for the industries, big industries. As the current falls, then so does the demand. As the demand falls, so does the electricity bill. So when you reduce to correct or improve the power factor to bring it to unity or as close as possible to 1, then you use less electricity, you pay for what you use actually, and your current is going to be reduced, and you don't need as big of a cable sizes as you did before, and also the switch gear, and your bill is going to reduce. That's the essence of power factor improvement. So again, the analogy, this is a low power factor, very bad one. The power factor is low, like 0.7. This is an average one, and this is a high power factor, or the best one that we can get. For instance, is 99%, maybe 0.99. So that is how good it is if you improve your power factor to as close as 1. Questions. Name and define all types of electric power. Can you do that? If you can't, you have to go through the lesson again and understand the lesson. What is power factor and what is the best power factor to have? Remember that? It's 1. If you don't know why, go through the lesson. Or how can we save on our electricity bills? And then finally, write the formula for true power, reactive power, and apparent power, and what are their relationship, or what are they measured in, and their units. First question, name and define all types of electrical powers. True power, the measure of the power used. Reactive power, the power in terms of inductive or capacitive or wattless power. Apparent power, combination of true and reactive powers, and it's measured in volt amps. What is power factor and what is the best power factor to have? Power factor is the relationship between true power and the apparent power, or cos phi, and best power factor is 1. How can we save on our electricity bills? By improving the power factor to unity. Write the formula for true power, reactive power, and apparent power, and what are they measured in. Their units are as follows. True power, volt times current times cos phi, is measured in watts. Reactive power, Q is volt times current times sine phi, and is measured in volt amp reactive. Apparent power, S is volt times current, and is measured in volt amps. And the other formula for it, if you have these two powers, true power and reactive power, you want to find the apparent power, is basically using Pythagoras, square root of all of this in bracket, P squared plus Q squared. Now you should be able to define different types of electric power, define the difference between them, define power factor, and explain why it's important to improve it or correct it. And some of you can now explain how we can save on our electricity bills and also write the equations for all types of power. Well done. Any questions? Any comments? Please write them down and I'll get back to you as soon as I can. Thank you very much.